just consider another models, and today I'll present a little bit another results, and I'll show you later. So, what is the agenda for today? A little bit introduction about impulse response function, and then we built the estimator of impulse response function. And the idea of this estimator really lies in the work of Valery Buldygin, and this attempt to estimate impulse response function as cross-correlogram belongs to Valery Buldygin and his schools. But in another situation, so in another inference. We consider such estimators, but with different processes, with different situations, and start analyzing its properties. And we will speak about unbiasedness, consistency of this estimator, and of course about the rate of convergence of the estimator of IRF function. And then we try to use this rate of convergence to construct, to build the hypothesis testing on the impulse response function. And at the end, I'll show you a little bit small example on simulation study. So about the idea, the philosophy of impulse response function. And so impulse response is the reaction of any dynamic system in response to some external change. So, and it characterizes the system's behavior in time domain. That's why if we consider just, it could be like a shock, like direct function, but it could be with some lagging effects, with effect that can be on some interval, or just the values of this influence can be longer. So we will operate such definition like input. We have input on the system like process X of t. Then some transformation, it should be something happened, and output. So, and the idea, can we, knowing the input and the output of such transformation, estimate what had happened here in this black box? So it's a very common formulation of this problem, and there are a lot of different directions how can be it solved. And in our case, if we consider just direct function, then the output should be like this transformation function, h of t. That's why if we consider linear time invariant system with x of t like input process and y like output process, then the output process can be presented like convolution of input process and this transformation h of t. So the idea is to connect input and output process in the form of convolution. So there are some common properties that should be mentioned. First of all, this is causality. The system is causal, is called causal if h of t equals 0 on negative semi-axis. So, and it means that it doesn't respond before the impulse occurs. So first the input process, then we have the reaction of this process. We will consider only a stable system. It means that it should be bounded input and bounded output process. And that's why this condition should be true. That's, we suppose that this function h of t contains all information needed to predict the response of any input. So, and there are a lot of many applications of such systems with input-output process and some transformation, and it could be considered in signal processing, in economics, in medicine, in ship dynamics, in climate and ecology, oceanologies, in big data as well. So the applications of such ideas would be found in different spheres. So, and what about the result that we will start work with my supervisor Yuri Vasilievich Kozachenko? So we suppose that we consider such situation also linear time invariant system with input process x of t, some transformation h of t, impulse response function, and output y of t. We suppose that our influence, that our action could be made on the finite domain 0 lambda, and we consider only the action on this finite domain. So we suppose that this response function 0 otherwise except this domain, and it should be belong to L2 process, L2 space, so it two-time integrable. And then the reaction of the system y of t can be represented like such integral from 0 to lambda, our impulse response function, and the input function. So and the tau. So we have such lagged effect that during this interval 0 lambda, there could be influence on this output process y of t. So, and we suppose that our process x of t is a stationary centered Gaussian square integrable stochastic process, and it perturbs this system 1. So then our main question is how to estimate or identify the function h by observations, input and output. So we suppose that we know information about the input and output process and want to estimate h of lambda, and then find accuracy in the field in the space of continuous function. So it's a probability that supremum of difference, this function greater than epsilon, to estimate this probability, and the norm in LP processes. And if we can do this, then it's easier to say about the goodness of p-test for the shape of the impulse response function. So, and first of all, we just separate the empty signal on this interval 0 lambda, and each with a star, it means that we just subtract our input empty signal from our impulse response function. And as I said, the estimator of this function, impulse response function, h of star, we will consider like cross correlogram between input process x of t and output process y of t, and like integral from 0 to t divided by t, where t is a parameter for averaging. And this is the idea of, yeah, and it was discussed also in the work of Valery Buldygin, and not only Volodymyr Zayats and so on, the group of researchers that work together with Valery Buldygin. So, but in their case, they considered the family of input processes perturbed and consider their properties. In our case, we consider another situation. first of all, I just want to mention that all integrals in my talk means like mean square Riemann integrals, and they exist if and only if there exists such integral concerned with covariance function of input processes, and we suppose that it is finite. So, and the idea that distinguish our results from old results of variable Deakin, that we consider another input processes. We also consider family of input processes, but this family are obtained by so-called model or decomposition of input process by, for example, Fourier orthonormal basis. We consider just a finite sum of transformation of decomposition of input process, and this parameter n plays important role in all these estimators and rate of convergence. So now we suppose that the input process can be considered like a model of ideal input process, yes, and this n it's very important now in our work. So we have to put some condition. First, these conditions on input response functions, analytical. So we suppose it's pretty rough, but it's now we suppose that it's two-time differentiable on this integral, and there is some constant here, which can be concluded if we know this function. And the condition B means that we do not have any influence over this interval 0 lambda. So we suppose that all influence had been met at the end of lambda. So that's why our function h of 0 should be equal to h of lambda. It's a technical condition that we can also can be just follow up, but now we will prove all these results with this condition B. So, and under these conditions, A and B, we find the estimator, the biasness. Yes, so this estimator is biased, and we can estimate, we can just say the upper bound of this biasness, and it is depend on some constants and depends on this parameter n that we have met in model construction of input process. And here we see that if we consider the case when n tends to infinity, so we obtain the asymptotical unbiased estimator of impulse response function. So from the inequality for it, it's clear. And there's also the bound on the variance of the estimator. And here we see that we should find some balance between t, parameter of averaging in cross-correlogram, and n. So not only n should tends to infinity, so not only the model, the property of model should considered, but the property of estimator itself should also be considered to say that this estimator is consistent, for example. Yes, the sufficient condition for consistent estimator that variance should tend to 0. That's why t square should tend to 0 if we want to obtain a consistent estimator. It's also clear that if we just enlarge this domain where we consider the influence of our input-output process, then we obtain the beta estimator of impulse response function. So the beta, it means consistent one. And the next theorem states that under assumptions A and B, the estimator h with the head is asymptotically unbiased and consistent as tan and t tends to infinity. So, and then we find the Hölde. We proved that this estimator stays the Hölde condition. So it means that the variance of the increments of this estimator is less than or equal than some constant c and the difference of time point tau and theta in the power of alpha for any alpha from 0 to 1. And then this this property for increments allows us to obtain the rate of convergence in the space of continuous function. And then we can say about the supremum of difference between our real function, input response function, and the estimator that is constructed like a cross-correlogram on the input and output process. So, and the technique of the proof of such theorem is the same like Yuri Vasilievich Kazachenko used about the probability of supremum of the tail of the distribution for different processes. And in our case, we use the theorem about square Gaussian processes because if we consider the estimator for impulse response function, it would be, if we centered it, it would be square Gaussian one because input process is Gaussian. The output process is also Gaussian because we consider linear time invariant system. And that's why estimator should be, with some normalization, a square Gaussian process. So, and then we use the technique for square Gaussian process for to obtain the norm in L-pair processes and L-pair spaces. And showed that the probability that a norm in L-pair in the power of p greater than epsilon could be estimated like such transform, such function J2.
And p is any positive number?
Epsilon.
P. Parameter p.
Parameter
Can
p.
it be fractional or?
P here? Yes.
Positive. Can be any positive number, real number.
Yes.
Okay.
So, and then if we have such distribution of the tail, some norm of these increments of the tail, then we, for difference norm, we can state the hypothesis testing. So the zero hypothesis, the main hypothesis, states that impulse response function is h of t, and alternative is opposite statement. So, and for example, like in Kolmogorov-Smirnov hypothesis testing, so we just consider supremum of the difference, the main function, the impulse response function, and the estimator, and say that with a given level of confidence, so delta now is a significance level, and 1 minus delta should be as large as possible, where delta is like small one. The hypothesis H no is rejected if the supremum of the difference between H tau and the estimator is greater than epsilon delta, where epsilon delta we can find from this condition on the rate of the convergence in the continuous space for our estimator. So, and otherwise, there is no evidence to reject alternative hypothesis. That's why we accept the main hypothesis. So epsilon delta is the root of such equation. G1, this function that bounds the probability, the tail of the probability of the continuous norm of the difference between function and estimator. And with given delta, with given n and t, we can find this epsilon delta, for example. In this case, it is obvious that the probability of supremum of difference greater than this threshold epsilon delta should be less or equal to delta. So it's like error of first type error in hypothesis testing. So we just bound this probability. And the same situation, but we just consider p is equal to 2 here. Yes. How can we construct the text, the test for in L2 processes, in L2 space of, for the estimator? With for given confidence level 1 minus delta, the hypothesis H0 is rejected if now we consider not supremum but the integral and the difference of estimator and real function h of tau with a square. Yes, so we consider such norm, and if it is greater than this threshold, then we reject the main hypothesis. Another, otherwise we accept H0. And the same as in the first theorem, epsilon delta is the root of the equation J2. J2 from this epsilon delta should equal to delta. So, and what is the simulation study? We consider one example. Just lambda equals 10 and alpha 1 with the impulse response function like tau, epsilon exponent in the power of minus tau minus epsilon exponent in the power of minus lambda, and just find all these constants that we have mentioned in the condition A, and normalize this function, just subtracting the empty signal. And then we have such situation that we can fix, for example, accuracy, epsilon. We can fix significance level delta, and we can fix n parameter, so the upper cutting level of our input process, and then we can find the critical value t. So it means this is the t under which if we have t less than this number on the table, then we can reject our main hypothesis. If t is greater, then we can accept the main statement, the main hypothesis, the zero hypothesis. So, and it could be found for, in table we have only finite values for accuracy and delta, but we can find according to the theorem or just computational skills, so we can find for any epsilon and delta this value. Or otherwise, we can fix t and find the cutting level n. So it's also can be found. So in this case, we have to fix this balance between n and t to obtain the appropriate level of the error for the first type. So, and the next table consists of such critical values of, for the second type criteria, for the tests that concerns of L2 norm for the estimator. So here is also the difference type of accuracy, and we see the more accurate we obtain the results, of course, the more T we should just find. So, and this simulation also can be considered in this graph, where we consider the cut-in level, upper level of input process, the composition, and equals 500, and consider for different delta, for different significance level, this function for accuracy. Yeah, of course, it means that the more accurate we want to obtain estimator, then more parameter we should find. So it's decreasing function. So, and about models, it's well-known book about that was motivated to published by Iryna Rozora simulation of stochastic processes, and some of our works which is related to impulse response function. The first paper was published in Theory, Probability, and Mathematical Statistics on cross-parallelogram estimate of impulse response function, and then we also consider another results in the Journal of Communications in Statistics, Theory and Methods. And together with my PhD students, Anastasia Melnik, we consider such a topic. And the last paper was together with PhD students, statistical estimation of hypothesis testing on the impulse response function. So, and this is the main part of my talk. It's not so large. That's why I want to promote the journal that I'm care of. This is bulletin of Taras Shevchenko National University of Kyiv, Physics and Mathematics, and it's great work of and Юрий Васильевич Kazachenko and Mikhail Pavlovich Maklachuk, because they were the editor-in-chief for a long time of this journal, and we are working together to make this journal visible in international spheres. And now I'm an editor-in-chief of this journal, and it's that's why I just want to say that we are waiting for your articles to be published in this journal. Now we are in Scopus, we are in quarter 4, and we are open to publish all the results that are good enough. So please, I invite you to be here. And this is all for this talk for today. Please, questions and comments.
Okay, thank you for your interesting talk. And yes, questions?
Yeah, here Volodymyr Anisimov. Do you hear me?
Yes.
Yeah. Hello, Iryna. I'm interested. What type of other input processes can be considered using this methodology?
We consider in this methodology, we consider just like decomposition of such input processes.
Yeah. But what type of another processes can be? Did you think about extension?
Yes, we consider some extension. We consider not only bounded processes. So here we just bounded our domain of the influence of impulse response function, and we have some paper that we consider not only zero lambda, but on the positive semi-axis, and also obtain. But the idea was the same. So we just want to decompose the input process on some orthonormal basis on this domain, and then we use such a technique. Yeah.
For example, can it be applied if input is Poisson process? It's quite natural situation can be, right? Or also more general control Poisson process.
Interesting questions. We do not investigate with Poisson or Poisson control processes, but it's really interesting to consider it.
Yeah.
Thank you.
Okay.
But sorry, Iryna, I missed the beginning. So yeah, it's very interesting question about input. So it looks like you consider just classical
Yes.
input for filtration, and what Professor Anisimov probably asked, it's like maybe Levy process or kind of non-Markov even. But what I'm missing, so impulse function which you are estimating is just some standard assumptions. It's just stationary linear input-output control system, or I miss something.
Yes, you're right.
But what I'm confused. Yeah, you showed that kind of very nice that you use time averaging and then proving all that wonderful estimates, kind of like Kolmogorov-Smirnov metric. But so it would be just in some sense it's just solution of Wiener-Hopf, I mean Wiener-Hopf of what integral equation, right? It's just it's what I don't understand. It's just you're recovering the kernel of singular integral equation of Wiener. I mean, I don't know. It's in English. Why Wiener-Hopf? Or in some sense, you're solving it. It looks like. With some statistical regularization, or I am confused.
Now I'm not ready to answer full of your questions, but it's very interesting to consider in such direction, and to compare maybe, and to be clear. Yes, where is our results and where is
what I'm kind of thinking with all your, like it's very simple to do it when you have linear control system with feedback and you have two polynomials, L P divided on by MP. Then you can solve easily, recover your impulse function, right? It's by definition, but it looks like you are recovering like in classical filter condition, that famous condition on spectral density. Or I'm mistaken? So something kind of, I see that kind of disconnect for me to understand where we are with your result.
So our result is that first of all we perturb a system with stochastic processes. So we consider not deterministic systems, but stochastic one with such processes, and I'm not ready now to compare with Wienerhoff
The
approaches.
factorization or whatever.
Yes,
Yes.
I'm not ready now to compare it.
Because definition is classical, right? It's just
Yes,
you
yes.
give delta function.
Yes.
It should be realizable
Yes.
filter when you. By the way, how you check that it's a realizable filter? Because it shouldn't decay very fast. Remember that famous Kolmogorov condition, integral of log of spectral density should be less than
Yes, 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 I
infinity.
understand.
Oh, you have some. So
Yes,
sorry,
yes,
I
we have. I think it will be enough here. So we have this condition on the variance of
okay,
the
okay.
increments, and on this situation, yes, it will be.
Okay, because I tried to connect, that famous condition when we can predict. I don't know. It's probably in Mascarapot with, but with you. Okay, I see. So actually, the most important kind of engineering that part of the slow decay at infinity for in frequency domain. You give it here via just variance tau and what is big lambda? It's interval for your averages, right? It's going to
No. T
no.
is a parameter of averaging. Lambda, it's a parameter where we
Okay.
consider such. So
Okay.
this
No.
is
It's
here.
so
Zero lambda
you're
for
just
this
taking
one.
T capital and
Yes.
okay.
Yes. Thank you for your interesting
Oh,
comments and
it's
questions.
just trying to understand that.
Yes.
And in chat, you have a question from Sergei Shklyar.
Just one moment. I want to share. If the parameter n is used in the construction of the estimator itself, what is each n? Just for construction, you mean about construction of estimator. Am I right? Each n is our bounded upper bound of biasness of estimator. Small hn, it's just this number. So how fast the estimator tends, the expected value of estimator tends to real number, real function.
Thank you. And is n used when you construct the estimator?
When we construct, so it is used, capital N, it is used in our presentation of impulse function, and impulse function then we use for construction of our estimator. So we just used it to model, to simulate the input process. Then we construct estimator on the model of the input function and output function.
Oh, and it's very interesting question. I just want to confirm. So n capital, it's in some sense how many harmonics we have to take, and
yes.
But with your simulation, did you check that ergodicity property, that your harmonics, how they distributed over unit circle? Kind of just if you display, would it be what is the proper word, ergodic, and kind of go over this, the whole circle uniformly?
In our simulation, we didn't do this, but
how big was your n? Let's say
n should be big enough. So in our model construction, if we consider our book with Yuri Vasilievich Kozachenko, n in different situation, it could be different, but it with large numbers.
1,100. I just
More than,
ballpark.
yes.
Or 10,000.
Mm-hmm.
Okay. And how long did you run it? Like if it's 10,000? I've never done simulation for.
It's too hard. 10,000, it's too hard. And that's why for simulation study, we take smaller sample. For example, 1,000, but it's too long also, 1,000.
But did you try to use some discrete fast Fourier kind of for calculations, 1/2n, and then trying to, because it's again, kind of something what is interesting. It's ergodic properties of those frequencies. It's like for Choplet's matrices, it was just what Polya he found, and then Segur he proved, and then Kolmogorov. So how then? I mean that it's what is the proper word for ergot? Uniform density that you can integrate over those frequencies. I'm just curious if, like 10,000, if we display it, I mean, how we can say that it's uniformly distributed in some sense. It's what, okay, so sorry, it's just, again, I'm asking probably kind of, yeah,
so
very interesting.
It's good field for thinking and to investigate later and deeper. Thank you a lot.
And Professor Maybarada wanted to say something.
Yes, please. So you have proposed two tests for testing hypothesis on the function h. What you can say about the power of these tests? What alternatives they can capture?
We in this direction we consider only the type of one error, yes, which is bounded by a delta. About power, it's a good question, but it seems to me that this test should be consistent, so power should tend to 1.
It is maybe the key question for the practical application. What are the alternatives for which you recommend this test? You see, and the second question is on the case when you observe the output with some noise, with some error. Will your estimator deteriorate in this case, or it will work good also when some noise is added to the output?
I think it should be something stable condition. I think it depends. So from my point of view, we can consider output process with some errors, yes, and control this variance of errors. And I hope that this method could work with errors as well.
Okay, thank you.
Thank you.
And then I will ask, and you can play with this P. If P equals infinity, then you obtain this uniform norm.
This P, yes.
Yes, and if you have a power of the test, then you could recommend which P to select for your test.
Yes.
It
Yes.
would be interesting.
Thank you. Thank you for comments.
And not only alternatives, but local alternatives could be interesting. And not only consistency of your test, but you can calculate the power under local alternatives. And can we imagine goodness of fit test?
What do you mean, imagine?
Can we create a kind of goodness of fit test? So we have certain observations and we are not sure that they have this form, and you can check, is it your data fulfilled this model or not?
I guess yes. We can try it. But so it's there are a lot of work to do this about goodness of fit tests. But yeah, I think we can do this.
But it's probably difficult to implement. Now, completely stupid question from my days when I did functional analysis. Could it be extended just, it's like pure mathematically, like Orlich spaces, you know, some kind of, or have you,
yes.
I mean,
I think yes, because the norm of in Orlich space for feasible Gaussian process, for square Gaussian process, we can obtain, and that's why we can extend these results for space of in the norm of Orlich. Process.
Why I asked, because you know, I recently I saw some papers from Italy where they used in credit risk metrics Orlich spaces. So and it's I know the guy, he's accountant, but he likes mathematics. So I think that even it would be interesting. I mean, I believe it would be interesting to understand how can I say the different embedding of functional spaces, and how it would go into such asymptotic results. Because I don't think it could be used like implementation. It would be kind of difficult, right, to do any such hypothesis test, and it's more like you're doing to confirm your asymptotic result. Okay.
Thank you.
See another question from Professor Prakasa Rao in chat.
Just one moment. There are several methods of the convolution in the era of density estimation. Can such methods be used to estimation of impulse response function? I think yes, of course. The methods of the convolution also can be used for estimations. It's different approaches of the same problems. Yes.
But
thank you a lot
which
for
method is better? How to compare?
To compare. Good questions, but it depends on what we have and what we want to do. Yes, and what
The rate of
estimate.
convergence.
Yes.
That should be compared.
Yes. Compared. Yeah. So.
And what about asymptotic normality? Is it possible to get?
Yes, I think that in the paper of Valery Boldygin, they consider most of their results were considered by asymptotic normality. Not in such formulation of problems, they consider another family of processes that perturb the systems, but they obtained asymptotic normality, and that's why I think it could be also considered like asymptotic normality. I didn't prove it, but I think it could be.
And then you can construct confidence intervals or even confidence stripes for your function.
No, it's another question, right, from Professor Rao. Oh, I'm mistaken.
Another, go. Can we use kernel method for estimation of impulse response function? Kernel method, I didn't use it, but I think yes, we also can use kernel method for estimation of impulse response function.
Any other questions? And then thank you once again for interesting talk. And
thank you a lot for being here, for your questions and for your discussions. It's very fruitful and useful for me.
Thanks a lot. Thanks a lot.
Maybe Igor, do you want to ask something more?
Oh, no. I just wanted to ask about that journal because, Professor Kukush, I told you about that averaging techniques and theorems which I proved, a long time ago. Maybe it's the good opportunity for me. Just I want to translate in Ukrainian, maybe send it to Iryna's journal. Iryna, it's just mathematics, physics, and
computer science,
like,
yes.
Pogolubov averaging, new methods of continuation by parameter for control systems, right? It would be a proper kind of venue.
Yes, of course. We consider different.
The only one thing I need to check, is it more like theoretical, or you could present some simulations results? What kind of purpose of the journal? It's just pure mathematical
it's wide.
journal.
No, it's not only pure mathematical, because we cover not only mathematics fields but computer science, and there are a lot of also publications that cover simulation methods as well.
So it could be theorems with simulations.
Yes.
Okay,
yes.
Thanks a lot.
And I want to make another announcement. And now I am a member of editorial board of Ukrainian Mathematical Journal.
Oh,
and this journal has Q3.
Oh, wow.
Yes, it is a bit large, stronger than your journal.
Yes, you are stronger, but you're older.
I think, yes, and I will be responsible for probability and mathematical statistics with some other colleagues of mine. And you're welcome to submit papers. We have no restriction on the length of the paper, and we accept English papers and Ukrainian also. And the English version of this journal is published by Springer. Ukrainian version is published in Kyiv by the Institute of Mathematics, and then Springer publishes.
By the way, Professor Kukush, it's kind of interesting with Ukrainian mathematical journals that online, for example, I was able to download first Geekman papers after the war, what he published about his dissertation, and it's wonderful with use of averaging. But there is some gap, what is online from, I believe, 57 to 70 or whatever. Could you somehow ask, I understand that it's a lot of work, but I think it would be useful if somebody would you know, put online, or I don't know even if it's available in Kyiv
It is available
library.
in the library.
It's
Recently,
available.
I was looking for a paper of mine dated 1985, and they had
85?
only
Yeah.
1985, yes, in
Ah,
Ukrainian mathematical, and they had only paper copy, and then they made pictures and sent to me as their
yeah.
files with my paper.
Because, for example, when I was young, I saw that first in Kyiv the university edition of that. It's not journal, but published by Kyiv University. The first book of Bogolyubov Krylov on averaging, and it was called longitudinal stability of airplanes or something, and it was I mean this the introduction was typical for us who lived under that in Soviet Union, that now it's very important for goals of Communist Party to model airplanes, and after that it's all that beautiful Bogolyubov theorems of everything they were presented. So I believe that it's kind of some unique literature, the same as Ukrainian mathematical journal, because, for example, I couldn't find some papers of Sokolov. It was famous, at least kind of in Kiev. Yeah. But thanks, it would be interesting. So it's available. If I am in Kyiv, I can go to the library and check. So,
And see the comment in chat about Bogolyubov Krylov.
oh,
No,
okay, okay.
it was a joke that airplanes were relevant then, drones are relevant now. No, it was a joke.
No. It's with drones, and it's a long story because I did it for rockets. Well, you know, for liquid fuel rockets. And what is interesting that just today I found that it was beautiful. I mean, it was done only in Ukraine, and Russians, they have it. It's so-called Satan rocket with minimum start. I don't know, when you would throw the rocket to the air. I mean, from the mine, and it would launch when it's 200 meters above the earth, its engines. But you know, you know, my father was part of that project. Yangel was, I mean, but now it's Russians. I don't think they can use it because they need space engineers. But what is amazing, there were many mathematical problems regarding that how you would get that rocket out of the mine because of you know that hole or diameter, how you could do it precisely, and it was famous mechanical engineer Professor Krasovsky who solved it. But I mean, I was thinking about drones, and could we use today? It looks like our Bulava. Maybe you heard the drone Bulava,
Yeah.
and then Anduril. They use it's exactly that technology. They use metallic containers. They would throw a fixed wing drone, and then it would open its wings, and it would fly. So, yeah, but exactly. Bogolyubov Krylov extension is very important for drones, and especially 3D printing drones, because they're made out of plastic, so you have all those longitudinal oscillations. So Yeah. Professor Yanis, you're some applied mathematician. I'm just curious why you were
Yes, mathematical physicist. Now I'm in computational finance. I'm based in the States, in New York.
Oh, okay. I'm in Florida. Yeah. Computation. Yeah. So do you work for some bank or some, I mean, well, in terms of
I used to now I have my own research firm.
Okay.
There is an interesting interplay between computational finance and fluid dynamics. People can have learned about fluid dynamics from trying to simulate to solve computational finance problems. There was some
and the equation of Black and Scholes was invented in this way, from fluid dynamics to finance. And Black
yes,
is a physicist, I think.
yes,
No. It's kind of funny because Black, he even didn't know that it was heat equation. It was Merton who recognized it. It's
Yes,
kind of
yes.
when Black he came up, he and he had good education, but he had not recognized that it was just heat equation, and he just needed to solve it for those boundary conditions. And yeah, it's, yeah, to what Professor Yanis he said, especially that link we can see when we can see the American options, because for American options it started from Merton. He helped Paul Samuelson to solve with
Yes.
Warren that first, and if you check that paper, it's reference to exactly McKean, you know, that famous McKean,
Yes.
McKean, he solved it, and he referenced that he used some techniques in some engineer, I mean, or in some techniques from mathematical physics.
And next time we will have a talk by my former PhD student, Andriy Malenko, and it is about radar systems.
Oh, so it was what he. Oh, it's a wonderful. Yeah, it's a wonderful paper. You have probably to. Yeah. It's looking forward because it. I believe it uses principal components for because it's a wonderful. I believe kind of applied statistics result.
Yes. So you're welcome next
Okay,
week.
thank you.
Okay, then we will finish our wonderful meeting. Thanks a lot.
Thanks a
Thank
lot,
you a lot.
Elena. It was kind of interesting when you get such rigorous functional. I mean, I don't know how to call that area, but from pure applied problem.
Yes.
Thank you a
Okay.
lot.
Thanks. Bye.
Bye.
Bye.